It's now time to lay out the corrective deformation plan. Corrective deformation is also known as post-space deformation, or the acronym PSD. For faster communication, from here on out, I may use the acronym PSD or PSDs in place of its longer equivalent terms. If you've been keeping up with this course, you should recognize this table from lesson 28, where I discussed the pros and cons of the corrective deformation options I was considering for this character. I have since then evolved this table into a diagram on the Lucid app. The Lucid app is an amazing tool that lets you draft bubble charts and other cool project planning diagrams. I've placed the link to their website up on the screen. In addition to the main solutions discussed in the previously introduced table, this solution tree introduces some additional solutions that I've decided to explore for corrective deformation. Let's discuss the options presented and see what is going to work best based on performance and ease of setup. Let's look at what this solutions diagram inherited from my previously introduced corrective deformation table. Traditional blend shapes, advanced skeletons joint-based skin controls, and sculpt deformers, which I originally planned to utilize directly on my skin mesh. Now let's take a look at the newly added solutions I've included. In-context blend shapes, clusters by way of an intermediary blend shape or by way of advanced skeletons custom cluster control. Soft mods by way of advanced skeletons custom soft mod control, and sculpt deformers by way of an intermediary blend shape. Even though some of the new additions appear to be a hybrid or alternate version of the original three, what I've essentially done is added 2 additional deformer types to the original 3 that I started with. Here's a list of the 5 deformer types: clusters, soft mods, joint-based skinning, blend shapes, and sculpt deformers. Now, the order in which these deformers have been presented on screen is no coincidence. They have been listed from the least to most computationally expensive and resource intensive. In lesson 28, I talked about deciding what to go with based on ease of setup. But now, I realize how easy the deformer is to set up is irrelevant compared to its expense on memory. If you sat through the face building and troubleshooting lessons, you may have noticed that the rig has slowed down quite a bit. Here's a comparison of the rig before and after the head building process. Look at the playback frame rate. Notice the considerable drop in the frame rate. This is happening because it is now processing more complex skinning and math to make the head rig work. If I want a responsive rig, I simply can't just utilize the most expensive deformers for my PSDs. So what this means is I will look for every opportunity to use soft mods and, more importantly, clusters to resolve corrective deformation wherever possible. Let's go over a quick definition and performance summary of each of the 5 deformers. A cluster is a straightforward deformer that transforms a group of vertices based on a single handle's movement. It's very fast due to the simple mathematical operation of applying a transformation to a defined set of points. A soft mod is a powerful, non-linear deformer that applies transformation with a fall-off, similar to a proportional editing tool with history. It is considerably more computationally intensive than a cluster because it involves more complex calculations over a defined fall-off area. Skinning, as you already probably know, computes deformations by blending the influence of multiple joints on a single vertex. It is generally efficient, especially if you're using linear blend skinning. Now, it's important to point out that for this rig, at least for the body, we used the dual quaternion skinning method. And dual quaternion skinning is slightly slower than linear blend skinning. I'm guessing for the face rig, Advanced Skeleton probably used linear skinning during the build process. But even with that consideration, modern GPU implementations of joint-based skinning are highly optimized. So skinning is still third on this list for least computationally expensive. Number 4 on the list is Blendshapes. Blendshapes achieve complex deformations by interpolating between a base mesh and one or more target shapes. The primary expense is memory usage because each blend shape target requires storing a full set of vertex position data. Now in Maya, blend shapes are generally more computationally expensive than skinning, especially in a real-time context like a video game engine. The performance difference, however, depends heavily on the specific implementation. But taking into consideration the high resolution of our mesh and the number of active blend shapes this character is going to need for optimal corrective deformation, the computational cost of blend shapes for this project is clearly going to exceed that of our skinning, even though we have quite a bit of joints and are utilizing dual quaternion skinning. Lastly, the most expensive, the sculpt deformer, applies a deformation effect to a mesh based on an influence object with a defined radius. Like a soft modification, it is categorized as a non-linear, high-cost deformer due to the calculations involved in applying the effect across its area of influence. Now, in spite of this close comparison to a soft mod, sculpt deformers are significantly more expensive. The performance difference comes down to how each deformer calculates its effect on the mesh. The table showcased on the screen lists some specifics about why the sculpt deformer is more expensive. I'm going to leave it up on the screen so you can take a screen grab of it and do some further reading about the differences between the two. So, amongst many things, you might be wondering, what is the difference between these duplicate solution types that use the same deformer? We have in-context blend shapes and traditional blend shapes. Then we have clusters via an intermediary blend shape versus advanced skeleton clusters. And finally, we have sculpt deformers applied also via an intermediary blend shape versus sculpt deformers applied directly to the skin mesh. In Maya, a traditional blend shape system is one where blend shape targets are derived from duplicating the source mesh. On the contrary, an in-context blend shape system does not require targets to be duplicated. As long as the source mesh is in edit mode, targets can be sculpted directly on the source mesh, and changes to the source mesh's vertices happen as an offset. The changes are stored as delta values on the target node. The workflow to draft in-context blend shapes is significantly more intuitive than that for drafting traditional blend shapes. For the previous version of this rig, I did all the blend shapes through this traditional intermediary blend shape target. In this showcased video snippet, I'm sculpting a corrective blend shape with the traditional blend shape approach. I'm sculpting my results on my target, which was duplicated from the source or skinned mesh on the left. To see my results on the skin mesh, I have to have the skinned mesh posed in a different window to see how it's receiving changes from the target. This is a horrible way to make and assess changes. To do the same thing with an in-context blend shape, all I have to do is activate a blend shape node created on the skin mesh, pose the character, and sculpt my changes directly on the skin mesh. Way more intuitive and hassle-free. This is particularly great because, as I mentioned in lesson 28, blend shapes are the go-to deformer type for complex deformations. This significantly better approach to creating them will facilitate the production of the complex corrective deformations that this rig needs.